All right. So today our topic is going to continue what we started talking about before our test yesterday, and that's drawing shear and moment diagrams. And what we talked about or started talking about Monday was how to construct these diagrams using a graphical approach as opposed to actually using method of sections, cutting the beam, and getting the equations for the shear force and bending moment, and then graphing those equations. Hopefully today we're going to get to the point where we can draw these without having to calculate those equations. So quick reminder, the one thing we talked about Monday, today's Wednesday, was if we have a beam and we have a concentrated force or a concentrated moment, acting at some point A, we looked at, in general, what effect that concentrated force and concentrated moment had on the shear and moment diagram. Not going back through this, but just remind you, what we found was that for a situation like this, if we've got a concentrated force, then we saw that the shear force V is going to go down whatever magnitude that force is, right, at that point where it's applied. Now, remind you, the opposite would happen if that force was acting up. If the force at A was directed upward, the shear force would go up, whatever that concentrated force is at that point. And the same thing would happen to the moment diagram. The moment here, for a counterclockwise moment, we saw that the moment goes down, whatever the magnitude of that applied concentrated moment is at point A. And again, the opposite would happen if our concentrated moment applied at point A was clockwise. The moment diagram is going to go up, whatever the magnitude of M8 is. Right? And so that's what we went through and proved this on Monday. And we're going to use that along with what we're about to talk about coming up next. All right, but any questions about that result that we went over on Monday? All right. Well, so today what we're going to talk about is what if we have an arbitrary distributed load. If I can spell distributed. Instead of just a force concentrated at one point, what if we've got a force spread out over some length? So what we're looking at now is if we've got this beam. Again, we'll just look at one simply supported, pin support roller, and we've got some arbitrary distributed load acting on this beam. So this is just some distributed load. We'll denote with lowercase w for our distributed load. And what we want to do is come out here some arbitrary distance x and cut some little infinitely small section of this beam. It's got some length, what we'll call dx. Right, so we're gonna cut this beam, and we're gonna look at this little section of the beam. And so I'm gonna come over here and draw a bigger blown up picture so we can see this a little better. All right, so this is our little piece of beam that we're some arbitrary distance x from the end of this beam, and we're going to look at this little section. And so we've got this distributed load that's acting on this little section of beam. And so the magnitude of our distributed load at this point would be whatever this function W is evaluated at that distance x. And we want to see how does the shear force and bending moment change from this surface to that surface, the left side versus the right side. So we're going to have some shear force, call it V, some bending moment M that's acting on this surface, that cross-sectional area of our beam. And we're going to have a shear force and a bending moment acting on this cross-sectional area, surface of the beam. And so we'll call this shear force V plus dV. So the shear force here is going to be equal to whatever the shear force is there, plus some change. That's what the dV here represents, the change from the magnitude of shear force here to the shear force on the right side. Similar notation with our moment. The moment here is going to be equal to whatever the moment is on the left side, plus some change in moment we'll call dm. All right, so that's basically my free body diagram of this little piece of the beam there that we cut out, showing our distributed load acting on it, and shear force and bending moment on the left side, and shear force and bending moment acting on the right side. So our goal is to find what's the change. How much does this shear force change? How much does that bending moment change? If we know that, we're going to get a nice result we can use, and so save us a lot of time and effort calculating these equations. All right, so what we're going to do first is you've done in statics, we've done in this course. When you have a distributed load, we want to replace that distributed load with some equivalent resultant force. Now here's where we're going to use the fact that we're looking at a really, really small length or width here, that if dx is really, really small, in fact, if dx is infinitely small, right, so this distance dx is infinitely small, then we know our distributed load, W, is not going to change much at all over this infinitely short distance. So this distributed load is essentially or approximately constant over this little distance dx. And that will be true for any distributed loads that we see. Now, yeah, theoretically, can I have a function here where this would not be true? Yes. You know, mathematically, if I happen to have like a vertical asymptote there, then that function is going to change significantly over an infinitely small distance. But we don't have distributed loads in the real world that do that we're going to see acting on a beam. These are going to be nice, smooth, distributed loads. And so as long as we restrict, ourselves to the kinds of distributed loads we would see in a structures environment, then this would be true. Well, if we assume that distributed load is constant, then that resultant force is just equal to whatever that distributed load is times that length dx. Remember, for a distributed load, the resultant force is equal to the area under the curve. Well, if we assume that essentially this is constant across here, the area is just height times width. So that resultant force, again, is just the distributed load times this distance dx. Right? So now we're ready to apply our equilibrium equations. We'll start with summing the forces in the y direction. Set those equal to 0. Excuse me. So I've got v, I assume, is going up. We've got v plus dv going down, so that would be minus that force. And then we have our resultant force from our distributed load also acting down. So we'd have minus this distributed load function times that length dx. And all that is going to add up to 0. Those are only three forces we have. The shear force on the left side, shear force on the right side, and our resultant force from our distributed load. Well, when you distribute this negative sign, we're going to have v minus v. Right? So those two essentially cancel each other out. And we're going to have minus dv minus w times dx equals 0. So we have minus w dx. If I move the minus dv to the other side, it becomes positive. So that's what we're after, is the change in the shear force. Now, we're going to see this relationship maybe today. Hopefully we'll see it. We'll get to this. I'm going to use this to do something else. But for now, if you just solve for w, you get minus dv dx. And I'm going to use that relationship to show something else that we may get to today. We'll see. But for right now, what I want to do is take this relationship and I'm going to integrate both sides. And we want to go from, we got some arbitrary x value here we'll call a, and some arbitrary x value here we'll call b. So we're going to integrate both sides from x equals a to x equals b. And so I'm going to put the dv on the left side. So we're going to integrate dv, and I'm going to pull the negative sign out here. And on the left, we're integrating with respect to v, shear force. So we would go from whatever the shear force is at A to whatever the shear force is at B. Now on the right side, we're integrating with respect to x. So we're actually going from x equals A to x equals B here. Well, the integral on the left side, if you integrate dv, you get v. And then you evaluate it from VA to VB, you wind up with VB minus VA. Now on the right side, what we have is the integral of this distributed load function from x equals A to x equals B. Well, you think back to calculus, just in general, when you integrate a function from x equals A to x equals B, what you get is the area under that curve from x equals A to x equals B. So what we have is minus the area under this distributed load curve. So our shear force is going to change from whatever it is at A to whatever it is at B by taking whatever the shear force is at A and subtracting the area, again, under that distributed load curve. This is the result we're after. So if we have a distributed load acting on a beam, then I know the shear force is going to basically go down. In this case, negative, so we're going to subtract whatever the area is under that distributed load curve. Now, go back up to previous discussion, right? The area under this distributed load curve, that's just that's the resultant force. And so that sort of agrees with what we talked about up here with our concentrated force, right? V goes down, whatever that concentrated force is. Same thing's happening here. V is going to go down. So V goes down whatever amount equal to the resultant force, again, which is the area under that distributed load curve. Now, how it goes down, we'll talk about a little bit more here in just a minute. And just like I mentioned previously with that concentrated force, what we just did, we had our distributed load acting down. And so it goes down. We're subtracting that. If our distributed load was directed upward, just like with the concentrated force, the opposite would happen. The shear force would go up, whatever that area is under the distributed load curve. Again, it goes down here because I applied my distributed load acting down. The opposite would happen if it went up. All right, any question about that result? All right, no question. So let's sum the moments. So we need to pick a point to sum the moments about. I'm going to pick this point here. I'll just call it point O. So we want to sum the moments about point O. Set that equal to 0. I'm going to choose counterclockwise positive. Now, before we sum the moments, go back and do one thing up here. This goes back to, we assume that the distributed load was constant over this little distance dx. Well, if it's constant, that means our area is a rectangle. And we know in general, a distributed load, that resultant force, acts at the centroid of the area. But for a rectangle, the centroid is right in the middle, halfway. And so not only do we know the resultant force, it's going to act at right in the center. Ex over 2. That's where our resultant force acts. All right, so now let's sum the moments. So summing the moments about point O here. I'll go right to left here. We'll start with this one. We got M. What's dm? All right, that's that moment. Counterclockwise, we're going to have, well, let's go over here. We got this M going clockwise. And we're summing the moments about point O, so this force goes through point O, but this one does not. V over here does not. So that's minus clockwise moment V times this distance dx. And then we got our resultant force counterclockwise. All right, that's the force. And it would be times dx over 2. Now it's got to add up to 0. Well, remember we said dx was infinitely small. So if we look at this term here, right, that's w times dx squared over 2. Well, if dx is infinitely small, you square something infinitely small, you get something really, really, really infinitely small. And then we're going to divide it by 2 and make it even smaller. So essentially, we're going to neglect that term and say it's essentially 0. Right? This term is so small, we're going to neglect it. So what we're left with is the stuff over here to the left of that. Well, again, we got an m, we got a minus m. they cancel each other out. And so what we have is dm minus v dx is 0. Or if we solve that for v, we get dm dx. Again, this is a relationship that I'm going to use to show you something else if we have time today. But what I want to do now is exactly the same thing we did up here, and that's integrate both sides. So if we integrate both sides, again, from x equals a to x equals b, on the right side, we've got v dx. Again, this is from x equals a to x equals b. And we integrate, we get mb minus ma. When you integrate dm, you just get m. And just like we did up here, if we integrate this shear function v, what we get is the area under the, if I can spell, area under the shear curve. So our moment changes from whatever the moment is at A to get the moment at B along this beam. We add the area under the shear curve. So basically the result of this is we know our moment is going to go either up or down, whatever the area under our shear curve. And so this is how we're going to use the shear diagram to draw the moment diagram. We know the moment is going to go up or down, and whether it goes up or down is whether the area is positive or negative, and you'll see that in just a second. In fact, let's see if I can find. I think I've got. This would have been maybe, I don't know, when we first started talking about shear moment diagram by calculating the equations. And we went back and looked at this previously when we illustrated this what we talked about on Monday. So I found that same picture again. And so we had this this beam with those loads on there. And we went through and we calculated those equations. But I pointed out the other day, we got this concentrated force of 30 kilonewtons. Our shear diagram goes down 30. We come over here, we got this concentrated force, By was 56. Our shear diagram goes up 56. And then our concentrated force of 50, it goes down 50. And we wind up same value as our support reaction there. Right? But what I want to point out now is a little bit different observation. Right? What we just proved was that the moment is going to increase or decrease by the amount under the shear diagram or shear curve. So look at this area. We'll call this A1. Well, what is that area? Well, it's 1 meter wide. It's 30 tall. So the area is 30. Now, it's negative, right, because it's below the line ABCD. So it would actually be negative 30. Well, look at what our moment diagram did. We started at 0. And what did we do? We went down 30. That's not a coincidence. We just proved in general that it's going to do that every time. Right? Look at this area. We'll call this A2. This is what's 26 by 3. So A2 is 26 times 3. Do some math in my head. 52, 78. Well, look at what our moment diagram did. We went from minus 30, and we went up to 48. How far did we go up? 78. Same as that area. This time we're going up because the air is positive. It's above the axis. All right, and then finally, we'll call this A3. A3 is negative. Right, it's below the axis. And it's 24 times 2, which is 48. So we go down 48, wind up back at 0. So we can get our shear diagram from the loading. We get our moment diagram from the shear diagram. And we don't have to calculate any equation. Right, so everybody follow that? Anybody, any questions about that? We're going to work one from scratch here in just a second. All right. Okay, then we will move on. And let's see if we can do this one. Got a beam. Got a pin support here at A. Roller support at this end, B. And we're going to put some concentrated force, P, acting right in the center of this beam at point C. It's right in the middle. This beam's got some length L. That would be L over 2, and this is L over 2. All right, so we got a nice, simple supported, simple example of a simply supported beam. Got concentrated force applied in the middle, and again, we want to draw the shear and moment diagram. I reckon that would be diagrams. All right, that's what we're going to do. Draw a shear and moment diagram. So we need to know what our support reactions are. Now we're going to have vertical support. Not AY, BY. Just an observation, it's a pin support. You could have AX, but we don't have any forces in the X direction. So AX is 0. So I'm not even going to put that on there. And I would hope by looking at this just from symmetry, you should be able to look at this and tell me what AY and BY are. If P is applied right in the middle, AY is going to be equal to BY, and it's going to be P over 2. So we can get those just by using symmetry and observation. This is P over 2, and this is P over 2. Any question about how we got those support reactions from symmetry and without having to do any calculation? Y'all are being awful quiet today. Nobody's asking any questions today. I don't know if that tells me y'all not paying attention, or maybe I'm just doing such a great job at explaining this. Let's see if somebody's alive. Let's see. Adam, you're on top of the list. Can you unmute yourself and at least say something?
Yeah, I'm listening.
Okay, I just checking to make sure that, that everybody's out there. All right. All right, so that's basically all we need to construct our shear moment diagrams. But I do want to touch on one thing that I think somebody mentioned this or asked about this. This was back, my days are all running together, about how the moment would be, we knew the moment would be zero at the ends of this beam. And so maybe we go back and sort of discuss that again for just a minute. So let's look at end A here. And this is certainly, you don't need to go through and do this every time. But I want to go through it at least once here, and so you'll kind of see how we know what's happening at the ends of the beams. If you came and cut this, if we're looking at the end of the beam, here's A. So if we cut this as close as we can get it to A, again, infinitely small distance dx will come out there and we'll say, well, we know the support reaction is P over 2. So if you wanted to find what the shear force and bending moment are acting on that cross section, again, we can do it using method of sections, just like we did. We're going to cut it this distance dx. Well, I know the sum of the forces equals 0. So I know the shear force here has got to be equal to whatever that support reaction is. This is AY. Always. Right? And if you sum the moments about point A, what you would have is you'd have M, AY goes through A, and then you'd have minus V times dx. But again, if this is infinitely small, that's essentially 0. So the moment's going to be 0. Always at the end of the beam. The only way it would not be 0 is if you actually had a moment applied at the end of the beam. And there's two ways you can do that. So maybe sort of summarizing here. We know V is always going to be equal to whatever the support reaction is. And the moment's going to be 0 unless you've got a cantilever beam. You got a fixed support there. You're going to have a reaction moment. So the moment would not be 0, it would be whatever that reaction moment is. Or another way is you could just have, you could have like a pin support, but you might have some applied moment there. So those are the only two ways the moment's not going to be 0. Is there has to be a moment at the end of that beam. And those are the only two ways you're going to get one. Is if you have a fixed support or you've got an applied moment there. Okay? So that's just kind of a general thing to just keep in mind whenever you see a beam like this. If you look at it, it's pinned at the end. There's no applied moment there. I know the moment's going to be 0 at the end. The same thing at the other end, B. The moment's going to be 0 there. Right? So that's good to know. So that's how we find out if we did everything right or not, or if we made a mistake. Now, typically, what you see when shear moment diagrams are constructed, typically, you'll see them drawn just below the beam with the loading on there. And it's just for, makes things easier to see where everything lines up. So here, this is going to be the shear diagram. And I'm going to put the points along here that correspond to the points along the beam. Now, if we had numbers in here, we would need to put the units, either newtons, kilonewtons, pounds, kips, whatever. This particular example, we don't have units, we don't have numbers, so we can get away without having to put units on here. All right, so we're going to take what we've talked about and see if we can draw this, again, without having to do any calculations. We don't have to determine any equations. So here at A, I know the shear force is going to be equal to that support reaction. So it's going to start up here at P over 2. And shear does not change until the loading changes. So here in the middle at C, it's going to go down P. So if we're at P over 2 and we go down P, that's going to put me at minus P over 2. So what we're doing is, we're just going down P. It does not change until the loading changes, so it stays constant. And just an observation, again, this, that, the magnitudes of those better be the same. All right, so again, once you get the hang of this, it should take you like 10 seconds to draw the shear diagram. All right? But any questions how we got that shear diagram? All right, well then let's continue. We'll draw our moment diagram. Again, we don't have numbers, so we don't have to put units on here. And again, I'm going to label these A, B, and C so we got everything lined up. All right, so the last thing we talked about was how the moment is going to go up or down, whatever the area is under the shear diagram. So this distance is L over 2. This distance is L over 2. So I'll call this A1. A1, it's a rectangle, height times width. P over 2 times L over 2. That's PL over 4. So our moment in this case is going to go up PL over 4. Right? This area above the axis, right? This is positive. Now, we know what we just talked about. I know moment's going to start at 0. Right? The moment is going to be 0 at this end. And we're going to go up PL over 4. Now, here's where we probably not going to have time to talk about whether the graph is a straight line or a curve or whatever. Probably have to talk about that tomorrow. So for now, just take my word for it. It's going to be a straight line. It's going to start at 0, and we're going to go up to PL over 4 because that's what the area is. Now, A2, right, is negative. But it's the same. It's a negative PL over 4. Right? It's the area of a rectangle, height times width. We're going to go down PL over 4. And if we go here, again, we're going up PL over 4. Here, we're going down PL over 4. And that puts me right back to 0. Again, which, if you don't wind up back at 0, we know we did something wrong. Because I know the moment's got to be 0 at this end of the beam. Because it's just a roller there. There is no fixed support. There is no applied moment. So I know the moment's got to be 0 at both ends of this beam. And so it's really hard. Now, sometimes I'll see students where they do, 2 wrongs make a right, and you'll make a mistake, and you'll make another mistake, and you wind up in the right place. But that doesn't happen that often. You should know what the moment's going to be at the end of the beam. And so if you don't wind up where you're supposed to, you know you've made a mistake somewhere. And so you can go back and find and correct your mistake. So given this beam and this loading, really it should take you, probably 30 seconds to draw this shear moment diagram. We didn't have to cut it. We didn't have to find any equations. It's real simple. It should be. Now, but it takes practice. This is something you've got to sit down and practice drawing shear moment diagrams. You can watch me draw and say, yeah, that looks easy. But until you actually sit down and do some yourself, you're not truly going to, master this process. And this is one of the most important skills, really and truly, for you to learn in mechanics and materials. Is if you're going to analyze a beam, you've got to draw shear moment diagrams. And this is how we can do it really quick and easy. Because if we were going to, analyze this beam and calculate, what the maximum bending stress was, we need to know what the maximum bending moment is. Right? Well, it's PL over 4. It's going to occur right in the middle of the beam, and that's what I would use to calculate my maximum bending stress. All right? Any questions about this one? All right, so we got time. We're going to run through one more. This one maybe we'll go through a little bit quicker because one thing we don't have to explain what's happening at the end of the beams again. So everybody's got this. I can speak up or is it gone? All right, so let's see if we can do this beam. Again, simply supported with a pin support and a roller. And right in the middle here, we have an applied moment. And so this is a concentrated moment. Got some magnitude M. And we've got two concentrated forces, P. And we're told the magnitude of this moment is P times L. Just so we'll only have unknown P's in here instead of P's and M's. But again, that's given. Right? That's not something that you would look at and know. If you got numbers in here, obviously that would be taken care of. And we're told it's some distance L. Again, between each of those, the end and where the first P is, and then another L to the middle, and another L to that P, another L to the end. All right, so we want to draw the shear moment diagrams for this beam. Well, we need to know what the support reactions are. Technically, we could draw it just knowing AY. Again, AX is 0. We don't have any horizontal force. But it's always a good idea to calculate both of them here because, again, this is a good way to check yourself. If you know what BY is, we know the shear diagram should wind up at the same magnitude as BY. So that's why it's good to do both. So it doesn't matter which one we do first. I'll sum the moments about A, and we'll calculate what BY is. So we got BY times 1, 2, 3, 4 L's. And then we got these two forces P causing clockwise moment. So minus P times L minus P times 1, 2, 3 L. And then we got our moment is counterclockwise, so plus PL. And again, that's our moment. We were told the magnitude of that moment is P times L. And we solve for BY. I got BY was 3/4 P. if I did the math right. If somebody sees something, my equation I messed up, then speak up. And then once we got by, it's just summing the forces, and we can get ay. So we got ay going up, by going up, and then p and p going down. And solve for ay. I got 5/4 p. Right, so we know ay is 5/4 times p, and by is 3/4 times p. Simple 2D equilibrium, calculate your support reaction. Right? And that should be all we need to calculate, or not calculate, draw our shear and moment diagram. Again, I'm going to label these points so we kind of keep straight where we're at. Again, no numbers given here, so we don't have units. So at A, it's going to be equal to that support reaction, AY. So I'm going to start here at 5/4 P. Go straight across. It does not change until the loading changes. When we get to this force P, we're going to go down P. So if we go down P, if I'm at 5/4 P and I go down P, that would be at 1/4 P. Again, y'all check my math and adding fractions here. But we go down P, right? We go down whatever that force is. It does not change, stays constant until the loading changes. Now, notice when we get here to C, we have a moment, not a force. Now, from our discussion back was Monday maybe, we looked at a concentrated force and a concentrated moment. We saw that the moment didn't affect the shear diagram. So we don't change, we just keep going. Shear diagram doesn't change until a force changes. When we get here, we go down P. So if I'm at 1/4 P, I go down P, that's going to put me at -3/4 P. Right? Again, I'm going down P. And again, doesn't change till the loading changes. We go straight across. That checks. Here's my shear diagram. If we were doing this, that first method where we cut it and got equations, we would have to cut this 1, 2, 3, 4 times. Whereas here, we just drew it with minimal effort at all. Right? Any question about that shear diagram? Right? Well, we use that to draw the moment diagram. Yeah, I'm going to label our points here. So we know moment at the end is going to be 0. There's no fixed support here. There's no applied moment there. Moment 0. Now we're going to go up. Whatever this, we'll call it A1. Right, it's positive. It's above the axis. We're going up that amount. Well, it's height times width. Well, each one of these is L. And so the area is just going to be height times width. 5/4 P times L. So we're going to go up. And again, for now, it's linear. This is the first thing we'll talk about tomorrow. So it was going to go up to 5/4 PL. And it's up to you. I've seen some people like labeling these on the sides like this. Some people like putting them on the diagram by the point. Either way is acceptable. It's really just personal preference. But we start at 0 and we go up what that area is. Now, the next thing is we're going to, again, go up whatever that area is. And notice I only went to C because here we have a concentrated moment. That does affect my moment diagram. It didn't affect my shear diagram. Well, A2 is height times width, PL over 4. We're going to go up PL over 4. So if I'm at 5/4 PL and I go up 1/4 PL, that puts me at 6/4 PL at that point. Now here's where that concentrated moment comes in. Remember, if we had a moment that was counterclockwise, that means that our moment goes down. If our moment is clockwise, we go up. But for this problem, it's counterclockwise, so we're going to go down whatever that moment is. If it was clockwise, we'd go up whatever that moment is. So we're going to go straight down P times L. So that puts me, right here, we're going down whatever that moment is. In this case, it's P times L. So I'm at 3/2, and I go down PL, that puts me at 1/2. PL over 2. So that concentrated moment, we're just going to go straight up or straight down, whatever the magnitude of that moment is. And then now all we got to do is A3, that's the same as A2. We're going to go up PL over 4. So if I'm at 2/4 and I go up 1/4, that puts me at 3/4 PL. And then we know it's going to go back to 0, but always check yourself, because here's where you'll find out if you've messed up somewhere. A4 is going to be negative. It's below the axis. And it's going to be 3/4 PL, which is great for us because if I'm at 3/4 PL and I go down 3/4 PL, that puts me back to 0. So if you can find your support reactions, which everybody's supposed to be able to do, and you know how to construct the shear diagram from the loads, right? If you can do basic math and get areas, you can draw your moment diagram. Very straightforward. Any questions about how we constructed these two diagrams using this approach? And this is how I would expect you or want you to do it on the test. Unless I specifically ask you to calculate the shear equation or the moment equation. If I just ask you to draw the diagrams, this is how I want you to do it. If you try to do it the other way, this problem that should take you less than, I don't know, maybe 5 minutes, is going to take you about 20 minutes if you do it by cutting it and getting an equation. If you do that, you're not going to have time to do the test. All right, we're out of time. We're going to talk about how we know whether they're straight lines or curves. Another example tomorrow. But that's it for today. If you got questions about something, again, if you hang around, you want to stick around after I stop recording, I'll be glad to discuss anything you got to talk about. So unless somebody speaks up now, I am going to stop recording.